appreciate you all coming out here. Yeah, so this is Chris mentioned using here to summarize my life. I'm not sure I would have summarized it that way, but it was close enough. Chris talked about he really has this evolutionary approach to understanding how the brain works, and I'm actually probably the one speaker today who's contrary to that in some sense. I'm not trying to take an engineering approach to it. I'm a neuroscientist, but I'm a theoretical neuroscientist, and we try to decipher the theoretical components of how the brain works, specifically the neocortex. So in the next 40 minutes, I'm going to give you an overview of what we've learned over the last so many years. I've been told it's a mixed audience, so I'm going to try to keep it at a level that would be interesting and absorbable by anyone of intellect, but not necessarily neuroscientists. And if there's anything, it's a small enough audience, if there's anything that's really confusing, you just say, I'm lost, you can raise your hand and I'll address it, but I'll be around the whole day to answer any other questions. So, and I'm happy to be here to help Chris and others as you guys try to start figuring out how to get MSU more into the neurosciences. Okay, so these are the two basically guiding lights I've had for over 30 years in my career. I want to understand the operating principles of the neocortex. That's the number one thing. I fell in love with brains back in 1982, I think it was, or 81. And I said, I'm just going to have to work on this. I felt that in our lifetime, in my lifetime, we should be able to understand how the neocortex works, how the brain works. It was the most interesting and most important thing I could imagine working on, and I decided to dedicate my life to it. As Chris said, back in those days, in the late 80s, in the early 80s, it was really very, very difficult to do theoretical neuroscience. It wasn't even a recognized field, and no one really wanted to fund it at all. That's not true anymore. I also decided that if you can understand the principles of the neocortex, you could then build machines that work on those principles, and that would be very, very good. And Chris asked me if I would speculate a bit about that at the end of my talk, which I will. So just in case you don't know, the neocortex is about 80% of the volume of your brain. It's the big wrinkly sheet that covers all the rest of it. So the rest of your brain's like a post, and the neocortex is a big sheet that wraps around it. And the neocortex is the locus of all high-level intelligence, language. My neocortex is speaking and driving the musculature in my voice box. Your neocortex is listening. Everything you can tell me about the world is stored in your neocortex. It's the center of all high-level thought and planning. All mammals have a neocortex. Non-mammals don't. And although we understand we study a large parts of the brain, my specific focus is the neocortex and some structures related to it. Okay, so here's the way we go about it. And Chris mentioned this too in a little bit way. This is not biologically inspired. All of our work is very, very detailed neuroscience, anatomy and physiology. Everything we know about the brain and the neocortex, which is a tremendous amount, in my mind, is a set of constraints. And if you're going to have a theory about how this works, you can't ignore those. You can say, I'm going to not pay attention to X because here's why. But you can't just say, we reach in and pick out a few little facts about the brain and say, I'm going to build something that works like that. The brain is a set of constraints, and our goal is to understand it. So I spend much more of my time in the neuroscience world than I do in the engineering world, because we need to understand those constraints. From those, we can build a set of theoretical principles, and we can test them. We can test them both in the biology with experimentation, and also just the literature searching, because there's so much unassimilated knowledge about brains. But we have these theories, and then we test them. We test them primarily in my work in software. We emulate this stuff. Ultimately, this is going to go to silicon, but we're not there yet. We're starting some projects right now with some other companies to do that. So this is the process we go through. It's a bit of an iterative process. We've been doing it for many, many years. We've made a lot of progress on this, a lot. And so I'm going to tell you about that now. Here's the agenda for my talk. I'm going to spend most of it talking about the theory, the principles that we've learned about the neocortex. Very little bit telling you what does it mean to implement one of these things, to build this stuff and make it run. I'm talking a little bit about commercialization, because I believe it's important to build a financial base for this and get people interested in it. It really helps if you can turn this into valuable products. And then I'll speculate about the future of intelligent machines. So let's just go into the theory. What does the neocortex do? If anyone tells you the brain is a computer, they're wrong. It's not a computer. It is a memory system. It is a system. You're born with the neocortex. It doesn't know anything about the world, and you have to learn about the world through your experiences in life. Now, it's a memory system. The input to the brain, you might think, oh yeah, I've got eyes, ears, and skin. I got 5 senses or something like that. That's not true. The eye itself is a million sensors, so you have to think about it that way. That's what it is. There's a million fibers on the optic nerve. It is an array of a million sensors. Your cochlea is an array of 30,000 sensors, and your somatic sensors, your body sensors, is about another million. So you've got a couple of million sensory streams coming into the brain. They're coming in high velocity, meaning they're changing rapidly. It's on the order of a few milliseconds, 10 milliseconds, 100 milliseconds, constantly changing. And this fire hose of data is coming into your brain, and the brain has to build a model of the world from that. It has to learn everything that's out in the world about computers and rooms and chairs and coffee cups and cars and whatever. Everything you know, every word you know, has to be learned through this process. Now, the brain itself does several things. One is it builds this model, and one of the things I wrote about in my book is about how it's constantly making predictions. And this was a real insight to me. You're making predictions about everything you see, feel, and touch, hear all the time. You're not even aware of most of these predictions, but it's true. And that was a real key to understanding how the mechanisms, what kind of mechanisms you have to make predictions. Of course, when you make predictions, you can detect when things are incorrect, anomalies, and of course the brain takes actions. Not always. You can sit here doing almost nothing and being very smart. But occasionally it takes actions. I'm speaking right now, and those are the basic things that the brain does. Now, there's another part of this, which is in the neocortex also generates your behavior, and we'll talk about in a moment. Everywhere in the neocortex is generating behavior. There is no pure sensory, no pure motor areas. It used to be thought that way. And most of the changes that occur on your sensory stream are due to your own behavior, your own movement. So your eyes are moving constantly, your body's moving constantly. I'm hearing myself speak, so mostly what I'm hearing is my own actions. And so there's this huge loop that goes between the brain exploring the world through interaction with the world and coming back. And so that's part of the problem as well. So if you're asking what does the neocortex do, it's this. Basically, the neocortex learns the sensory motor model of the world. The term often used is sensory motor contingencies, but it's a sensory motor model. What is out there? What happens when I turn left and I go right? If I go out the door, when I make a right, I remember where the coffee was. These are all expectations. I've already built a model of this building. And how did I do that? And it's a sensory motor model. Okay, I'm not going to go through the top 6 principles, my top 6, okay, of neocortical function. And I'll stick by them. There's others. This is just the summary of the top items. One is, it's an online learning system. So I already told you it's a memory system, it's learning, so it's a learning system. But online is the term which means that it's learning continuously. There's no batch processing here. The brain doesn't store up some data and then later say, oh, let's go look at it. It has to process it as it comes in, moment by moment. And it has to deal with it on an online fashion. 2, we know that the neocortex is actually a hierarchy. It looks like a sheet of cells. It looks like this big sheet, and it is, but it's actually connected in this hierarchical fashion. This is sort of a cartoon drawing. There's in the human brain, there's speculated maybe about 100 different regions that are structured in this hierarchical arrangement, the way the connections work, very well established. And so when the information comes into this hierarchy, it flows up the hierarchy and it flows back down the hierarchy. It's a 2-dimensional hierarchy. We also know that there is a common algorithm. As Chris mentioned this in his introduction. There's a common algorithm. Everywhere you look in the neocortex, it looks the same. And it actually, surprisingly, it doesn't matter if it's vision, hearing, and touch, that all the regions are doing primarily the same thing. There's some exceptions, but the primary is that they're all doing the same thing. The way you process vision is the way you process auditory or somatosensory input. It's all the same. This was discovered not by me, but a guy named Vernon Mountcastle in 1979, who was the first guy who speculated about this. So we have this hierarchy of similar memory regions. And the question is if we can understand how the hierarchy works and what each of those memory regions is doing, and we're along with getting closer to understanding how the neocortex works. Well, we do know something about this. We know that the primary memory function in all these regions is a memory of sequences. It's a memory of time transitions, of patterns over time. Now, this may not have been obvious to you. It certainly wasn't to me when I first started working on this. But let me just talk about inference is basic pattern recognition. So you're inferring from my speech. You're recognizing my speech at inference right now. And when you look around the room, you're doing inference. Well, think about it. If you're trying to understand my speech, the words are basically very complex patterns in sequence. The order matters, the timing matters. You have to have a memory in your brain of what words sound like, and what rooms sound like, and what things follow what in context. Inference is all about temporal pattern recognition. When you touch something, it's the patterns in time. When you hear things, and even as you move your eyes around the room, it's patterns in time. And basically, inference is almost all temporal. It's temporal sequence memory. And when I generate a motor output, such as my speech, what am I doing? I'm playing back complex temporal patterns. And I've memorized these. I can repeat them. I can repeat them. I can repeat them. I mean, I have these things in my mind. I've memorized words and phrases and concepts, and I can play these things back in these very complex, you saw them, very detailed patterns of musculature being articulated right now. So the primary things the brains do, which is prediction, inference, and motor behavior, are all based on sequence memory. And that's basically what's going on in each region in the neocortex. The fourth item here, we've learned, and someone later today is going to talk about representations, we've learned that the way brains represent information is something called sparse distributed representations. Everywhere you look in the brain, you find many, many cells. You find few that are active and most that are inactive at any point in time. It's sparse. And it's distributed, meaning that there's always a bunch of cells active, but not many. Percentage-wise, it's very low. And it turns out that we now understand the properties of sparse distributed representations. I'm going to go through some of them, and it's critical. You will not be able to build brains without sparse distributed representations, and you will not be able to build intelligent machines without sparse distributed representations. I can tell you that now. Fine thing that I mentioned a minute ago, that all regions of the neocortex are both sensory and motor. Everywhere you look, even the primary visual cortex, there are cells that project to areas of the brain that generate behavior. In that case, eye movements. There is no purely sensory and there's no purely motor areas of the cortex. We used to think this. And so everywhere you go, there's this sensory motor integration going on, and we have to understand that if we're going to understand how the neocortex works. And finally, there's attentional mechanisms in the neocortex. How you can tend to part of your auditory or part of your visual stream, or zoom in and zoom out. There's these intentional things going through the thalamus and the neocortex, and that's also part of motor behavior. And so these are my 6 principles. We understand all of them to some extent. The best 3 that we understand are these ones here. These are the ones I have the best knowledge about: sparse distributed representation, sequence memory, and online learning. And those are the ones we're going to talk about in depth today. There's still a lot to be learned, but we're bidding to get the big picture here and understand all the components. So without further ado, I'm going to jump right in. We're going to talk about sparse distributed representations. We're going to start by contrasting them to computers. So I assume all of you know a little bit about computers. In computers, we use something called dense representations. And this is like we'll take a byte or a word, 8 bits, 32 bits, something like that, and we use all combinations of 1s and 0s. So anything from 0, 0, 0, 0, 0 to 1, 1, 1, 1, 1, 1, 1. An example is the 8-bit ASCII code we often use to represent letters. And there it is. The letter M is represented by 0, 1, 1, 0, 1, 1, 0, 1. Well, I can ask you, well, what are the meanings of those bits? There are no meanings to those bits. If I say, what's the 3rd bit in an ASCII code mean? It means nothing. It's an arbitrary assignment. Someone once a long time ago said, we're going to let this represent the letter M. And the computer knows nothing about that. It's all in the software in the programmer's head. So those meanings are assigned by the programmer. If we look in the brain, we find representations that are very, very different. They're sparse and they're distributed. So, first of all, there are many bits. And when I talk about bits, I'm always talking about cells. Cells and bits, same thing. Okay. So when I talk about there's some 1 bits, we're talking about cells that are active. 0 bits are cells that are inactive. So just use the language of computer science for the moment. So typically in a sparsely representation, you have thousands of bits, thousands of cells, and at any point in time, you have mostly 0s and a few 1s. That's why it's sparse. So an example I'm going to use for this talk, we're always talk about 2,000 bits, and 2% of them are going to be active. So you're going to have 40 1s and 1,960 zeros. Now, in this case, in all cases in the brain, the bits have meaning. They're not arbitrary. They don't change. The neurons actually learn to have some sort of meaning about the world. It can slowly change as you learn, but they're relatively stable. So they have this semantic meaning. What does that mean? Let me just give you an example. We wouldn't do this, but this is an illustrative example of how you might think about this. Imagine if I wanted to represent a letter with a sparsely distributed representation. I would then come up with 2,000 attributes for letters. I could say, well, what are the attributes? I could say they're vowels, they're consonants. What do they sound like? E's and O's and I's. Do they have fricative sound, a hard sound, soft sound? I might say, how's it written? Does it have descenders or ascenders? Is it a closed shape, an open shape? Where is it in the alphabet? And so on. And then when I want to represent a letter, I would pick the top 40 attributes that describe that letter. And that's the representation I would use. Now these have to be learned. We don't do it that way, but that gives you an illustration what it means to form a sparsely distributed representation. This is how brains form representations about the world. Now there's some really interesting properties of sparsely distributed representations, and there's a little sub-research field right now getting into this. I'm going to tell you about a few, but not most of them. So here's some properties. First property is, if I took 2 of these sparsely distributed representations and I just compare them bit for bit, if they have a 1 bit in the same location, that means they share a semantic meaning. They share some semantic attribute, and they're similar semantically. Now, this is not going to happen randomly, so even if I just have, in this example, even if I have 3 or 4 bits that are common between these two, that is highly statistically significant. It's very unlikely to happen by chance in any way. So we can immediately compare two patterns and say, how are they different semantically, how are they different similarly? And if they overlap in what we call Hamming distance, or Hamming space, same bits there, we say they're semantically similar. We don't have to have a separate data structure to do this. No one has, it's to be built into the machine. The second thing is, what if I ask you to store one of these patterns, and then recall it later to see if it occurred again? So here's a pattern, I want you to tell me if it occurs again in the future. So we don't need to save all 2,000 bits. All we need to do is save the locations of the 1 bits. And you can think this is actually connections between neurons. You might be putting this together in your head here. I'm using computer science terms, but we're talking about neurons, actually. So we're going to say, instead of saving all the bits, we'll just say, here's 40 indices, and I'll save the locations of the 1 bits. Now, if I see a new pattern, and I see 1s in those same locations, I know I got the same pattern because there's only 40 bits, and that's it. So that's good enough. That's going to work great. Now, what if I told you you couldn't save the locations of all the 1 bits? You could only save a few of them. And randomly, we're going to subsample. Meaning I'm going to say, okay, you can only save the locations of 10 of those 41 bits. And that's all you're going to get. And a new pattern comes in, and you say, okay, well, let me see. Well, those 10 bits are there. They're all 1s. So can I say it's the same pattern or not? He says, well, no, I can't, because you might say, because look, I might get the 10 that are right, but the other 30 could be wrong. It's very easy to show statistically that's extremely, astronomically unlikely to happen. And if you do make an error, it will be one for a pattern that is semantically very, very similar to the one you started with. So if I said, oh yes, this is the same pattern I saw before, it would be something semantically, meaning in the real world, similar to the thing I saw before. And that's good enough. In fact, we want that. That is the basis of generalization. My last property, the most detail I'm going to get here today, is one of union of membership. If I took a bunch of these patterns and I formed a union of them, I ordered them together, logically ordered them together. So now I have 10 patterns, let's say, and I'm going to order them. Together. I got a new pattern down here. Instead of having 2% of the bits active, it's going to have about 20% of the bits active. I just order them together. Now I can't undo that. I can't say, well, what were the original 10? Can't do that. But I can do the following, which is almost as good. I can say, here's a new sparsely distributed representation. Is it one of the members of original 10? And you say, well, how would I do that? Well, I could just look to see if the new pattern has 1 in the union. And if it does, I'm going to say it's good. It's one of the original members. Now, this is actually very, very likely to be true. It's a little bit surprising, all comes because of the sparseness. But I can tell you that, yes, this is one of the original 10. And if it made a mistake by some chance, you said, okay, it's a half of pattern 1 and half of pattern 4, which is very unlikely, but if it did, it would still be very semantically similar to the things that were in the original union. Now, what are we going to do with this? The brain uses this property when it makes predictions. When you make predictions, you don't actually always have a singular prediction. You don't always predict exactly what word I'm going to say or exactly what you're going to see. There might be multiple predictions you can do at the same time, but you want to know if what did happen was expected or not expected. And so when the brain makes predictions, it actually does a union of predictions. It predicts multiple things at the same time. And it can tell if what actually occurred was one of those or not. And this is actually going to be the basis of our sequence memory. Okay, so that's enough about sparsely distributed representations. We now want to talk about how do we learn sequences of those in the brain, in the neocortex. A little bit more neuroscience here. You zoom in on the neocortex, it's that sheet on the left there. If you zoom in on a section of it, it's about 2.5 millimeters thick. You see these layers of cells in the second image there. The layers of cells, this is everywhere. It doesn't matter what species you're looking at. It doesn't matter what part of the neocortex you're looking at. There's a few exceptions to that, but pretty much it's going to look the same. A mouse cortex looks just like a human neocortex in that small slice. Just a human's is much bigger in the area. So we find these layers of cells. What I'm going to argue here is that each layer is actually doing a type of sequence memory. I'm going to tell you how it does it. Now, if you zoom in on one of those layers, just one of those layers in the middle picture there, there's two kind of organizational principles. In the green arrow, we see that cells, those little circles of cells, the cells that are vertically aligned with each other, in these little microcolumns, have the same feed-forward response properties. They represent the same thing somehow. In fact, just some pattern from the world. But the vast majority of the connections are represented by the orange arrow, meaning across columns, across the sideways. And we see that everywhere. In the next picture, we show one of those cells. They're packed in there, about 10,000 per cubic millimeter. That's a typical pyramidal cortical cell. And there's a cell body, and then there's a big dendritic tree, the branching tree structure. All the positive inputs to the cell are on the dendrites. A typical cortical neuron is anywhere from 3 to 10,000 connection synapses on one of those guys, and they're all arranged along those dendritic trees. Now, for many years, people thought that the cell was just like a sum, And the vast majority of neural network models you'll hear today still like that. Like, oh, we have a cell body with all these inputs, we add them up, we do some sort of nonlinear output function. It's not true. We now know clearly that the dendrites themselves are active properties. They're active processing elements. And in the last picture, we show a picture of a real dendritic segment. It's about 40 microns wide in that picture. You can see along there a whole bunch of little synaptic spines coming off of that little segment. We now know that on a section of a dendrite, if you have a bunch of synapses active, meaning inputs that are active, at the same time, within some few milliseconds of each other, in close proximity, basically within about a 40 micron distance, that it generates a nonlinear event, essentially generates a dendritic spike, which makes a large effect on the cell body. So I can have thousands of inputs active on this cell all over this dendritic tree. If they're dispersed all over the place, it has almost no effect. However, if I have 10 or 15 or 20 aligned in a very close section and they all become active at the same time, it has a very large effect. We think of this as like a coincidence detector. It's a threshold detector. It says, if I have a number of these guys active at the same time, bingo, it's something I want to know about. So our question is how does an array of cells with those kind of neurons learn sequences? And so this bottom picture shows from our simulations, the artificial neuron on the right there, you can see the colored dots, those are like the synapses. They're arranged along these dendritic segments, and the blue ones are these dendritic segments, and they're like coincidence detectors. I won't go through all the details here. We picked thousands of these guys, we arrange them in layers and columns, and the question is, how does that structure learn sequences, learn the temporal characteristics of the world that's involved in it? And we think we know the answer to that question to a large degree. I'm going to start here by showing you this picture. Here's just, again, a picture of our sparsely distributed representation, but these are like little cells, little cubes. The red ones are the active ones, and the gray ones are the inactive ones. This is about a quarter of our 2,000-bit sparsely distributed representation. And so, but this is what it would look like if you look in the brain. Literally, you'll find cells that if you can see them, you'll see there's a very sparse activation like this everywhere you look. And at some point in time, you'll have a pattern like this. At another point in time, you have a different pattern. And over time, these things are changing very rapidly. This is what's going on in your brain right now as I'm speaking. These things are changing on the order of every 5 milliseconds. They're going bing, 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 like this. These distributed patterns throughout your brain, not just in one region, all over the place. And the question is, how do we learn the sequences like this? How do we learn these transitions? And the answer is, we don't do it in any centralized fashion. The brain does it a neuron at a time. And so what happens when a neuron becomes active, that yellow one in the middle there, it looks around for some other guys nearby and says, look, if you were active just a little while ago, then you're predictive of my activity. And if I see you again, I'm going to predict my own activity. And so if he makes a connection to some subset of the samples nearby, and doesn't have to connect to that many of them, puts them together and says, if I see this, then I will predict my own activity. In the neuroscience terms, it will be depolarized. It gets ready to fire. And that's in a predictive state. If you do this, and you show lots of patterns, and all the cells get activated at some period of time, they all learn to predict their own transitions, and this is what you'll end up with, something like this. In this picture, the red cells are the current input, and the yellow cells are the ones that are being in a predictive state, saying, I think I'm next. Why are there more yellow cells than red cells? Imagine if I trained this on a pattern A followed by B, and then A followed by C, and A followed by D. If I show an A, it predicts B, C, and D. So you got a multiple prediction going on here. This is what we call a first-order transition memory, meaning it can learn from one state to the next, and this is the beginning of sequence memory. Actually, it's very powerful, but we need something different. We need a high-order memory. The high-order memory is what you need. It means I want to be able to use patterns over longer periods of time. I have to be able to repeat elements. So imagine if I gave you a pattern A, B, C, D, and another one X, B, C, Y, and I show you, if I show you A, B, C, I need to predict D, and if I show you X, B, C, I predict Y. I need to have that's a higher order memory, that's like a fourth order memory. I need to be able to have patterns with longer periods of time. So this one doesn't do that, and I'll tell you briefly how we're going to go about solving that problem. If I take one of our sparse distributed representations, this guy here, just some random one, and instead of representing each bit by a cell, I'm going to represent it by a column of cells. And so now I have a column of cells, and I'm showing 10 cells above each of these bits. And so if one of these bits is on, one of these columns is active, I'm going to randomly pick one of the cells in the column. So those are the darkened circles. I take the exact same pattern at a different point in time and pick a different set of cells, or randomly pick a set of cells in the column. So now I have two representations of the same input, the same sort of feed-forward pattern, the same pattern coming in, but two different representations in context. There are actually 10 to the 40th ways to represent, in this example, to represent the same input in different contexts. So if I say the sentence, there are too many tutus to count, I just said the sound to in 4 different contexts. And you didn't get them confused. There was tutu, which is an outfit, there was two, the number, and there was too many. And in your brain, at some point, you have the same representation, because the same sound is in your ears. But someplace else, you have to have a different representation so you don't get them confused. And this is basically the mechanism which is going on doing that. Okay, if you'll just have to trust me, I won't go through all the details here, but if you combine this, so you take a layer of cells in columns with these properties, these learning properties, you'll end up building a very high-level sequence memory. You can do multiple simultaneous predictions. It's high capacity. This kind of memory, even just these 2,000 columns I've been talking about, can remember millions and millions of transitions. We build these all the time, so this is empirically proven. It's distributed. Think about it that way. There's no points of failure here, no single points of failure. I can drop out columns, I can drop out cells, I can drop out dendrites or synapses. It continues working up to a fairly high level of fault. And then it also does semantic generalization. The whole thing is built on semantic representations. I didn't tell you how they were learned. We do understand that. But the semantic representation, so if I learn how one object behaves, and now I see another object that shares some semantic similarity to the first object, I can apply the learning of the first object to the second object. Then I say, yeah, this is a little bit different, but I recognize the pattern, and I'm going to make a prediction, semantically generalization to the new pattern. And this is the kind of thing which kills AI. They can't do that kind of thing. It's built in you automatically. Okay, if you're really interested in this stuff, this is all documented on our website. You can read a white paper. Yeah.
Comment how to see the penetration of neural net. Because earlier, I think you just said if I want physiological old models, right, that there's a non-linear interaction in the neuron.
Yeah. So the question is, how is this different than traditional neural network? First of all, neural networks is a broad class of things. It's not one thing. There are many, many neural networks, and the vast majority of them, going back to the 40s and then perceptrons and modern in the 80s and so on, the vast majority have a couple of things. One is they have a completely unrealistic neuron, which we identified. That was the difference between the dendritic properties, which is critical. The second thing is almost none of them deal with time. They don't think about time at all. They're spatial classifiers. The vast majority of them have no concept of sparse distributed representation. So if you look at them, they don't deal with the sparseness and understanding how to build representations. So is the brain a neural network? Sure. Is this a neural network? Sure. Is it different than most neural networks? Yeah, it really is. And you might say, well, that's a big difference or a little difference. I think it's a big difference because it makes a huge difference in the performance of these guys. If you try to find the literature of neural networks that learn sequences, there is some. But it's very, very impoverished because they're just not very good at it, and they don't have any of these properties. So I'm not an anti-neural network person. I'm a brain guy. Those are neural networks. But the vast majority of neural networks don't incorporate those principles: sparse distributed representations, time, columns, column structure, high order, and so on. Okay, I'm going to tell you what it takes to implement one of these things today. We do this in software today. This is a typical example for what we do in my company. We have 2,000 columns. We have 30 cells per column, so we have about 60,000 neurons. We have about 5,000 synapses per neuron, about 128 dendritic segments. These are all very realistic numbers in the biology. Again, if you go back to traditional neural networks, very, very few. Almost none of those neural networks can deal with thousands of synapses. They have no idea what to do. They usually have like 1,000 or 2 or 5, something like that. And about 300 million synapses total. We run this all in software today. It can run on, we've optimized this quite a bit. We can run on a single core CPU. It takes about 100 megabytes of memory. And we can do, in about 10 milliseconds, we can do one inference learning step, which is pretty good. And this is practical, and we have taken that and we're running it. Now, unfortunately, this is only about 1,000th, very roughly, 1,000th the size of a mouse cortex and 1,000,000th the size of a human cortex. So although this is a very useful thing we've built, and it turns out to be commercially valuable, we got a long way to go. And there's no way we're going to scale this purely in software. It's just not going to happen. So there's going to be a future of a harder business building brains. But the good thing is we can build things that are practical today and work and reasonable speed. Okay, that's the implication. I'm going to tell you a little bit about commercialization of this. I'm not trying to sell you a product. But the idea is to understand that, A, what does this look like when someone tries to do something with this today? It's not just hypothetical, not just purely theoretical. And B, I think it is important that we start an industry around this because that's going to drive a lot of research for this. So what we've done is we've applied this in the space of big data. Today, big data is a big topic. People are collecting data from all over the world, all kinds of sensors. They put them in storage, and they use tools for visualizing it and making predictive models. The problem with it is that the models get old very quickly, so some engineer or computer scientist builds a model of something like some consumer behavior, and then 2 weeks later it's obsolete. And it takes lots of people. So this is really a broken system today. It's not working very well. In the future, what's going to happen, it's just going to be like brains. You can take data from the Internet of Things, millions and millions, trillions of things. You stream them into models, and they learn in an online fashion. And from that, you make predictions and take actions. And the key criteria here, you need a continuous or online learning environment because the data in the world is the model, the underlying structural world is constantly changing. And you need to have temporal and spatial models. Very, very few people do anything in the temporal domain. So that's what we've done. We built a product that does this. We call it Grok. It's an engine for acting on data streams. In this case, we take on the left side, we take structured and semi-structured data in records from streaming off of sensors and so on, one or more fields. We run them through a set of encoders, which you can think of as just like sensory organs. They take some physical attribute of the world, they turn it into a sparse distributed representation, just like your retina does or your cochlea does. And then we feed them into our this cortical model. There's a little bit more to it that I'm not showing here. We feed it into the cortical model, but exactly what I just showed you: 2,000 cortical columns, 60,000 cells. It learns the temporal and spatial characteristics of the data, and then it makes predictions and anomalies, and we can take actions in that. So a user basically says, here's some data, here's my problem. They define the problem. Grok finds patterns in the data, outputs predictions with probabilities, and then we're finding lots of applications: energy pricing, energy demand, product forecasting, anomaly detection. I'm going to show you one simple example so you get a sense of what this is. Here's a very simple example. In the field of energy demand response, you may not be aware of this, but large consumers of electricity, sometimes university campuses, maybe MSU, I don't know, they don't pay a constant rate for electricity. They have a constant negotiation going on with the electrical provider, utility, saying, you know, an hour from now or 15 minutes from now, if you consume X, I'll give you this price. If you consume Y, I'll give you that price. And this is called demand response. And so here's a typical energy profile, electrical energy usage of the factory over 7 days. You can see 5 days of declining productivity, it looks like maybe, and then a weekend where not much is going on. This is not a particularly difficult problem, but it's actually, we don't know what the data looks like in advance. This happens to be what it looks like. And the customer wants to say, okay, at midnight, this is a very specific customer. He said, at midnight, we want to predict the energy consumption in our factory for the next hour, for the next 24 hours, every hour for the next 24 hours. And so we throw these kind of data streams into Grok, and Grok comes back, and here it is. It's actually predicting, you can't see it, but it's predicting 24 hours in advance in this picture. And it actually is able to follow these patterns very well. And it can catch all, adapt very quickly. I won't go into any of that stuff. Here's another example. It's a little bit less obvious. So this has to do with a company that provides an online service for decoding videos, and they have to have a very fast response time. So someone sends them information, they have to respond immediately. And so they have to keep servers online all the time, waiting around doing nothing. It's expensive. They could predict their load better. They could keep fewer servers online, save energy, save money. And so this shows their actual and predicted peaky demand curve. And it's not an obvious pattern, but Grok is able to figure out pieces of this, and it's able to improve their, basically reduce 50% of their cost by doing a better job of predicting what the demand is going to be. I'll just give you a little technical view here. You know, these are the kind of tools we use when we work on this stuff. Just pay attention to the right here. This is a diagnostic tool. We can look inside the system, sort of like looking inside the brain. And these circles here, these are the 2,000 dots here are all the actual columns in this model at this time. And the green dots are basically saying these are columns or bits that were predicted and actually occurred. So this represents a time when Grok predicted one thing and it occurred. Those are 40 green dots there. And another example, I might have this. This is where Grok was predicting multiple things might have happened. Those are the blue circles. And a green circle is something that was predicted and did occur. A blue circle is something that was predicted and didn't occur. That's not a problem. That's just like one of the things that predicted occurred. That's a good match, perfect match. Here's another case where you actually have, in addition to the green, it predicted and did occur, and the blue, it predicted didn't occur. We have some red circles. Maybe you can't see them in the back. I don't know, but there's some red circles there. Those are things that weren't predicted. Those were anomalies, and they did occur. So here, even when something is anomalous, it's not like binary. It's not, you can go in and say, if you wanted to, you can dive into this and say, what aspects of this were anomalous, what aspects weren't anomalous. The brain takes advantage of this information, but it's there inside of this. Okay, I'm just going to end up with a few thoughts on the future of intelligent machines. Hopefully, I don't have a clock, so hopefully I'm on time here. There's two basic views. There's the bad view. Now, I'm not a science fiction guy, so I didn't know what any of these things meant until my engineers told me about this. But these are bad things. This is like Skynet's, like, you know, and that middle one there is the Matrix, and this is, I think, Arnold Schwarzenegger's the Terminator. These are like, you know, robots, computers running amok, dominating human life, and so on. We're gonna build intelligent machines. I'm gonna talk about it. But this is one view, which is sort of this dystopian view. Then there's the other view. Oh, we're gonna have like friendly, you know, C-3PO robot butlers, you know, walking around taking care of us all the time. And we're gonna be playing games with people like IBM's watching them. Maybe we'll find new ways of entertaining ourselves by putting things on our head. And then there's sort of the in-between, which is sort of like, you know, how? Well, it started out as a good idea, and then it kind of went bad. You know, it's got some psychological problems. So what can we say for certain? All right, let me just tell you what I think. I have some very definite opinions about this. I've been thinking about it for a long time. Here's some things that are definitely going to happen. One is, we can make artificial brains that are faster and bigger than anything that nature's created. There's no question about this. Faster. Neurons are really slow. Semiconductors are really fast, about an order of a million difference in their performance. We can make brains that are a million times faster than human brains. And why would you want that? Well, you wouldn't want that in something like C-3PO, which is dealing with the world like you and I are. You don't want to be going too fast. But in a world where we have entire artificial intelligence that's dealing with online data or, you know, machine-generated data, the speed could be very helpful. And so we're going to do that. We can make them bigger. There's no reason we can't make bigger memory systems. You know, the human neocortex, the mammal neocortex got big by just essentially replicating itself. It got bigger and bigger. But as I said, your cortex looks just like a mouse cortex. It's just a lot bigger. And so we can do that still. It doesn't mean that these are going to be instantly super intelligent. They still have to be trained. They still have to work in a world, in some world, and learn about that world. It's not like intelligence is not just a meter. You can make the memory bigger, but you still have to find a world that you can discover structure in. We can create different types of senses. We tend to think of like the human senses, you know, vision, we're going to make a computer that sees, or we're going to do hearing or touch or something like that. But we don't have to be limited to that. I already showed you a moment ago, we can take structured data from, you know, energy smart meters and feed it into something like this. We can do all kinds of very interesting sensors in the world that I think we can build intelligent machines that look at different parts of the universe than we do. And then the Internet of Things is this idea there's a trillion things that are going to be connected to the Internet, and I believe a lot of them are going to be connected to artificial brains. And then the whole field of robotics and fluid robotics. Today, you know, the field of robotics research is very early on, and today's robots are very, very primitive. They're not fluid at all. You know, a flea or a mosquito is elegant compared to anything any human has ever built. But the answer to solving this, I think, is also neocortex modeling and sparse distributed representation. So we'll have amazing robots. It may not look at all like a human. Okay, and then here's the last one on the definitely going to happen. I mentioned that neocortex is a hierarchy of memory regions that are connected together in your brain. That's the white matter, connecting them together. However, there's no reason they ought to be co-located. So you could actually build an intelligence machine where those different memory regions are distributed in different places and communicate over long distances. I don't know what that's going to mean. I don't know what there's going to happen, but it will happen. And I think it'll be very cool. We'll find out. Here's some things that might happen. I haven't really certain or not, but there's reasons that you can argue they might not happen. Will we actually have humanoid robots? I know a lot of people want this. I'm not actually sure it's doable, and if it is doable, maybe a long way away. But to get something that really passes as a human, you can have a conversation with, is going to be very tricky. There's a lot more to it than just the neocortex, and you have to sort of have a body and be a human and know all the things that humans do. It's not clear that we even want that, but it might happen. I don't think we're all going to have, you know, be plugging in every night to some, you know, computer, you know, mind meld type of thing. Now, I know someone's going to speak later today, I think, is talking about brain-machine interfaces that are extremely useful for people with you know, trauma and recovering functionality. But this idea that we're all going to be walking around half human, half brain, I don't think it's going to happen. I can go into it, but I can't be certain. I can't, just in the maybe category. Maybe will, maybe won't. Here's some things I think are absolutely definitely not going to happen. You're not going to be uploading your brain to a computer. I'm sorry if you were hoping that, if you read Kurzweil's book and you said, yeah, that's what I want to do. It's not going to happen. And there are reasons why you basically, that the memory in your brain, the memory itself is so intimately tied to the specific wiring. I mean, we're talking trillions of bits of memory in your brain. It's intimately tied to the physicalness of the biology in your body that no one's ever going to figure out how to recreate. So you're just not going to be doing that. You're not going to have evil robots run amok. This is a thing that people talk about a lot, but it's not going to happen. The thing we have to worry about in the world is self-replication. You want to worry about something? Worry about things that self-replicate. But intelligence is not something that self-replicates. It's, you know, I can turn them on, turn them off. They're not going to do anything. And then I don't believe in this thing called the singularity. If those of you follow this, this is the idea that once machines can build are smarter than humans, they can build some smarter machines. You know, there's runaway complexity of intelligence that we'll never understand. Again, not going to happen. I don't have time to go into great details about it, but essentially intelligence is not something that you just design and turn up the crank. It is a memory process, it's a learning process. We can build very, very big brains. It's still going to take a long time to train them to figure out how to do that. So it's not going to happen. Okay, so the question is, the last slide, why do we want to do this? Why should we, this is why build machine intelligence, or that's what we're talking about. I'm interested in brains just because brains are cool. It's the most interesting thing I can imagine working on. But what about the machine intelligence? Why should we do this? First of all, we can live better. There's no question about it. I believe that machine intelligence will have the same or larger impact on society that computers have had over the last 70 years. And I'm very, very confident in that. And I would argue that computers have been very beneficial for us. And I can go into all kinds of ways where intelligent machines will help us live better lives. But there's another part to it as well. You know, if somebody asks me, what's the purpose of life? Why should the future care about us? Why should 3, 4, 20, 50, 100 generations from now care about us? They're not going to like us because we've overpopulated the earth. They're not going to like us because we've put too much carbon in the air. They're not going to like us because, I don't know, whatever. But they will cherish our discovery and cherish any knowledge we've gained about the world. And we still do that today. We cherish people in the past who made major discoveries. And I think knowledge acquisition, to me, is what it's all about. Even if I don't know what the end game is, I can say that knowledge acquisition is a good thing. We ought to be trying to figure out what the whole universe is about. And intelligent machines are going to accelerate that tremendously. We'll be able to build machines that are 1,000,000 times faster than us, machines that don't get bored thinking about math 24 hours a day. And if we want to explore the universe outside of our solar system, I don't think we're going to be sending any biological humans soon, unfortunately. It's too far. Well, can we send intelligent machines? Yeah, we can do that. So to me, it's all about discovery, and that's what brains do. Brains are about discovering the patterns in the world, and by building machine intelligence, we'll be able to expand beyond our capabilities in doing so. That's it. Thank you.
Dr. Geyer and the zoology department, I'm going to be taking over for Chris until he gets back. We're running a little bit late, but no problem. Let's go ahead and take a question or two before we move on. Yeah, Jim.
That was a great talk. Thank you very much. You learned a lot. In your SDR model, you treat neurons as either on or off. But in reality, neurons have gradations of activity, right? So
yes.
Under one condition, one action potential will be the output. Under another condition, that same neuron will have 10 action potentials.
Yeah.
How does your SDR model...
I don't know if everyone can hear the question. Did you guys, everyone need to hear the question? Do you want to repeat it? I'll repeat it for the camera. I'm sorry. I'll repeat it for the camera. The question basically, in our activation model, it's a binary activation model. Cells are either active or inactive. Well, actually, it's tertiary because it's active, it's depolarized, it's in predictive state, and then it's inactive. And real neurons we know have a scalar output. It's also true. I didn't go through it here, but also true on our synaptic model, which I didn't get into, and so on. The answer to your question is the following. It's true in brains we have a scalar output to cells. In some cells, not all. But there's a huge amount of evidence that suggests that brains can do significant work. We know this, there's a fact, can do significant work even just on a single synapse. And so when you have distributed representations, the way it works out is you can do a better job if I have scalar activation. But because it's distributed, I don't require it. Remember, everything is stochastic. Every cell is stochastic. Every cell can be unreliable. The whole system still works. So I can't rely on that. I can get better by having a scalar output to a cell. But I don't require it. So we took the simplification saying, from an implementation point of view, let's go with binary activations and see how it does. And it does extremely well. I know I could do slightly better, somewhat better, if I had scalar activations, but it doesn't seem to be a requirement when you have a distributed representation. So it's a choice you can make. And brains actually do a lot with a single spike, but then they can refine their behavior with multiple spikes.
We better stop. Just move
I'm going to
on.
hear all day, so
Yeah.
for those who want to talk to me later at lunch or something, I don't know.
So we're moving from human. I can speak loudly.